Before I begin this discussion of area and the fundamental theorem of calculus, I want to take just a second to pop up some formulas that are important to this entire chapter, and then we'll move in. I just want to get them up. I'm not going to discuss them in particular. You've got the integration rules we've discussed recently. We've got the material that led to the fundamental theorem of calculus and how that's related to finding area under a curve. We've got the formulas relating to marginal analysis, and then after this we'll have a couple more formulas to add. So that's sort of a partially complete formula sheet that will be complete at the end of this discussion. And now let's jump into the discussion. We want to talk about the area of a region bounded by two graphs. It just requires a slight modification of the technique we've been using for definite integrals to find area under a curve. And then we're going to use that for a couple of business applications. So this is really not much new theory. It's just a little bit of a different way of looking at something and then applying it to another business application. So what we're trying to do, whereas before we were looking to find the area under a curve, now we're looking at the area between two curves. In that graph, you can see that shaded area is the area between a curve called F and another one called G. Notice that F is on top and G is on bottom. Finding an area, given what we already know, turns out to be extremely simple. For example, in this figure, all you really need to do to find that shaded area is to first find the area under the curve F between A and B, and then subtract off the area under the lower curve, and that will leave you with the shaded area. In theory, that should be very simple to do. We take the area under the upper curve, that takes you all the way down to the x-axis, and then we subtract off the area under the lower curve. Upper curve area is represented by the integral of the top function, which is the f from a to b, minus the area under the bottom curve, or the lower curve. In that case, that would be the g function from a to b, and that gives you the area between, which is what we're looking for. So the area between two curves, where there's one curve on top the entire time and the other's on bottom the entire time, is just the difference between the two, top minus bottom, integrated from A to B. Very simple. And if you're looking at it graphically, that area between is the definite integral of f minus g, f being the top curve, g being the bottom curve, evaluated from A to B. Very simple. Let's look at some examples. The simplest case I can think of, both the graph and the interval are given to you, and one curve is always on top in that interval. Simplest case I can think of. In this case, f is the top curve and g is the lower curve. So we're going to integrate from 0 to 2. Those are the limits that we're interested in. And it's always top minus bottom. F is the top one. G is the bottom one. So we take 3 minus 1/3 x squared. And we take 1/3 x squared, which is g, and we subtract top minus bottom. Luckily here, that simplifies very nicely, because minus 1/3 x squared minus another 1/3 x squared is a minus 2/3 x squared. So you get 3 minus 2/3 x squared as the integrand, and the limits of integration again are 0 to 2. That's an easy one to do. The integral of 3 is 3x. Then you've got the 2/3 times x squared. The integral of x squared is x cubed multiplied by 1/3. And of course the 2/3 has to be multiplied in there as well. And 2/3 times 1/3 is 2/9. And we want to evaluate that from 0 to 2. That means you put the 2 in first for x, and you get 3 times 2 minus 9/2 times 2 cubed, minus, then we put 0 in. Luckily, everything zeroes out. They're all zeros, so that makes it very nice. So you just end up with 3 times 2 is 6. 2 cubed is 8. 8 times 2 is 16, so you get 16/9. You got 6 minus 16/9. If you don't want to put it in WebAssign like that, you can get a common denominator and simplify it further, and you'll get 38/9. That's the area between those two curves. Just a slight modification of what we've already been doing. How about this one? Sketch and shade the region bounded by the graphs of y equal 32 minus x squared and y equal x squared. Now this time we're not given the graph, so we have to figure out what's going on here. You don't have to sketch the entire thing, and in WebAssign you'll probably have like choices A, B, C, D, and you can choose which one it is from there, but here we don't even have that. But you do need to know enough of it to know if one's on top all the time. So what I would say about this is that y equal x squared is that parabola you've been dealing with forever in algebra and pre-algebra. It sits at the origin and opens up. Looks something like that. And y equal 32 minus x squared, since the coefficient of the squared term is a negative, you know it opens down, and that 32 pushes it up to 32 at the vertex. So the vertex at 32, but it's opening down. So when you push those two together, you can see that the parabola that's opening down is always on top in that shaded interval. But where are those intersection points? It's easy enough to find. All you have to do is take the two functions and set them equal to each other. So looking at the bottom one, if y is equal to x squared, you can put x squared in place of y and get x squared equal 32 minus x squared. Move the minus x squared to the left to make it a plus x squared, and x squared plus x squared is 2x squared. And that leaves the 32 on the right. Divide both sides by 2. You get x squared equals 16. So x is plus or minus 4. So now you know that the left-hand intersection point has an x value of minus 4, and the right-hand endpoint has an x value of positive 4. So that tells you you have to integrate from minus 4 to 4, with the top curve minus the bottom curve. So we're set to do that now. Again, it's the top minus the bottom. We're going from minus 4 to 4. The top curve is the 32 minus x squared. The bottom curve is the x squared. And we're going from minus 4 to 4. 32 minus x squared would be minus 2x squared. And the integral of 32 is 32x, and the integral of 2x squared is 2x squared divided by 3, which is another way of saying 2/3 x cubed. And you're evaluating from minus 4 to 4. Now, I've mentioned this before, but if you notice some symmetry in a graph, you might be able to simplify your work. And I noticed that the blue area, the shaded area on the left side of that shaded region, is going to be the same area as that on the right. In other words, there's symmetry here. So if you want to avoid going from minus 4 to 4, you can do it by going from 0 to 4, but doubling your answer. Because whatever answer you get from 0 to 4 is just half the entire area. So if you just do that and double it, you'll have the entire area. And we've talked about that before. And that's easier to do. It's easier to get a 0 in there. So to evaluate it, you put the 4 in for x and get 32 times 4 minus 2/3 4 cubed. And then you put the 0 in, that's all going to zero out. And that 2 that you're using to double is just sitting there waiting to be multiplied in at the end. So if you get rid of all those zeros, it's a very simple expression already. 32 times 4 is 128. 4 cubed is 4 times 4 times 4 is 64, times 2 is 128 over 3. You could type it into WebAssign like that, or you can get a common denominator of 3, do the subtraction, multiply by 2, and you'll get 512 thirds. Again, WebAssign doesn't require you take it all the way to the end there, so you could stop earlier and put in an unsimplified but correct answer. This is all very straightforward, but it does take practice. And I want to end with the business application. This is something you may have heard of in an economics class. It's called consumer surplus and producer surplus. I'm going to talk a little bit about the theory of it, but when it comes right down to it, we're not interested in this math class on the theory of what it all means and how it's set up. We really want to, in the end, get the formula we need to plug into and use it. So I'll set it up and how it works, but the important part comes later in just taking the two formulas and using them. But anyway, if you've got the demand curve for a product and the supply curve, the point they intersect is called the equilibrium point. Economists call the area of this region bounded by the demand function and the horizontal line where P is equal to P0, they call that the consumer surplus. On the graph, it's that region I've just shaded in or hatched in. That area is called consumer surplus. It's really the difference between the amount consumers would be willing to pay for something and how much they're actually having to pay for the product. That's the consumer surplus. On the other hand, the area bounded by the graph of the supply function and that horizontal line, that same horizontal line, P equal P0, and the vertical line, X equals 0, that's called the producer's surplus. And that's the region I've filled in below there. That's the producer surplus. Producer surplus is the difference between the amount a producer receives for selling a product and the minimum price needed to get the producer to supply the product. That's called the producer's surplus. And as I said, in this class, we're not particularly interested in the theory of all of this, how it comes about and where the formulas come from, but we do want the formula so we can use it and calculate these two quantities. So moving along, these formulas are consumer surplus is the integral of the difference between the demand function and P sub 0, which is the y-coordinate of the equilibrium point. And if you simplify it a little bit further and go ahead and integrate that P0, the integral of P0 is P0 times x, and we're going to be plugging x0 in it, which is the x-coordinate of the equilibrium point. So the simplest you can possibly write that consumer surplus is what I put in a box here. It's the integral of the demand function from 0 to x sub 0, where x sub 0 is the x-coordinate of the equilibrium point, minus the product of P0 and x0. That's the x and y coordinates of the equilibrium point. So it's very easy to calculate, and you'll see when we do an example. Similarly, the producer surplus is fairly simple, and it's the difference between the P sub 0, which is the y-coordinate of the equilibrium point, and the supply curve. And if you simplify that in the same way I did the other one, the simplest way you can write it is in the boxed in formula at the bottom. It's P0 times x0, which is the y and x coordinates of the equilibrium point multiplied together, minus the integral of the supply function from 0 to x sub 0, and again, x sub 0 is the x coordinate of the equilibrium point. So those are the two formulas that we want to use. So all the development of it is nice enough, and if you've taken economics, it may look familiar, but we want to take those two formulas and learn how to use them. So let's take an example. Suppose the demand and supply functions for a product are given by demand is P equal negative 0.36x plus 9, and supply function is P equal 0.14x plus 2. P is the price in dollars, and X is the number of units in millions. So the X is like the X coordinate of a point, and the P is like the Y coordinate of the point. Find the consumer and producer surpluses for this product. Either way, consumer first, producer first, it doesn't matter. You're going to need the equilibrium point for either one. So you might as well take that as your first step. Go ahead and find the equilibrium point. That's where the demand and supply functions intersect. So if you take the demand and supply functions and set them equal to each other and solve for x, you can add that negative 0.36x to the other side, making it a positive 0.36x, and then subtract a 2 from both sides, and when you simplify that, you'll end up with 0.5x equals 7, and if you divide both sides by 0.5, you get x equals 14. That is the x coordinate of the equilibrium point, what the formula calls x sub 0. To find the p, you take the x and plug it back in either supply or demand function. It doesn't matter which one you plug into, because at the equilibrium point, the two p-values are going to come out the same. So pick the one you like best, plug 14 in for x, do the arithmetic, and you'll find out that the equilibrium price, it's like the y coordinate of the equilibrium point, is 3.96. So that is your equilibrium point. Remember, the 14 is what the formula calls x sub 0, and the 3.96 is what the formula calls p sub 0. So if I wanted to do this now and find the consumer, say I want to do the consumer surplus first, I write down the consumer surplus formula, plug in the numbers, and do the integration. So x sub 0 is 14 and p sub 0 is 3.96. So if you plug in the 14 for the x sub 0, plug in 3.96 for p sub 0, 14 for x sub 0, and plug in the demand function, which is negative 0.36x plus 9 inside the integrand, that tells you what you've got to do. It's pretty easy. Negative 3.6x is going to integrate to negative 3.6x times x squared over 2, or 1/2 x squared, and that negative 0.36 just sits there. The integral of a number is just a number times x, so the integral of 9 is 9x, and you want to evaluate that from 0 to 14, minus the product of the equilibrium price and the equilibrium quantity, so that's 3.96 times 14, which turns out to be 55.44. So now we've got to evaluate that expression that we have here in the beginning. So you want to plug 14 in for x, and you're going to square it, plus 9 times 14. Notice when you plug in 0, everything zeroes out, so you don't have to worry about that. And then at the end, you've got that minus 55.44. You can type this in unsimplified with WebAssign to the extent that it will let you do that. But if you keep simplifying, and I'm not going to bore you with the arithmetic here, you'll end up with 35.28. That's the price in dollars, so $35.28. If we want to do the producer surplus, we use the producer surplus formula. Notice that in the consumer surplus formula, the P0 minus X0 comes at the end, and in the producer surplus formula, the P0 times X0 comes in at the beginning. But again, we've already found the equilibrium point, so we can put in the 3.96 and the 14, and we already multiplied it together in the other part. We already know that's going to be 55.44, and the integral is going to be the supply function this time, and we're going to integrate it again from 0 to 14. The product of those numbers we already know is 55.44. The integral of x squared is x squared over 2, so it's going to be 0.14 x squared over 2. The integral of 2 is 2x, and now we evaluate it from 0 to 14, which means we plug in the 14. The 55 minus thing just sits there, but make sure you put brackets around that numerical expression that you're going to write down to the right of that minus sign. Otherwise, you may mess up with your distribution and get a sign wrong. When you plug 14 in, it goes in place of x, but when you plug 0 in and put it in place of x, the whole part goes away because 0 squared is 0 times that number is 0, and 2 times 0 is 0. So that comes out really nicely, and that gives you 13.72 plus 28 to the right of the minus sign. And if you finish the arithmetic, you'll get $13.72. So the consumer surplus is $35.28, and the producer surplus is $13.72. And as I said, we're not that much interested in the interpretation of that. Save that for your economics class. But we are concentrating on doing the calculation correctly. So focus in on practicing that calculation and getting the consumer surplus formula down and the producer surplus formula down and not mixing them up. Otherwise, this is a very straightforward topic. And I'll close with finishing out our formula sheet. That's the same thing I started out with, except I added the stuff at the bottom that we just talked about here. That is sort of the encapsulation of the formulas that you need to know from this chapter.